and today we have minimum time to repair cars. And there's been a pattern in dailies for like 4 days, which is questions that are actually not directly a binary search solution. I'm just gonna save you all some time and tell you that this one also works with binary search, just like the one called Coco eating bananas. It's the same idea, more or less. It has this format where I'm just trying to give you guys a hint where when you know that's when you use binary search. It has this format when you say, well, it says it gives you an array. So here there's an array ranks representing the ranks of some mechanics, and then a mechanic with rank R can repair n cars in r times n squared minutes. So every mechanic can repair n cars in r times n squared minutes. You're also given an integer cars representing the number of cars waiting to be repaired, and it wants the minimum time to repair all cars, taking into consideration that the mechanics can repair all the cars simultaneously, so they can be repaired at the same time. The thing here is, the idea is, it gives you this array, right? And then it wants the minimum time to repair all cars. It wants the minimum something, or the maximum something. And the minimum time to repair all cars, you're gonna have to find a way to distribute these cars over these mechanics, right? And that you would never find a solution like this. Like, you would never find a way to solve the problem. If you would think, okay, this mechanic takes 2 cars, this mechanic takes 3 cars, yada yada, it never works. You're never gonna find a solution like this. You're gonna have to brute force it, check all the car possible counts against all the ranks, and then see what happens, right? Which is never gonna pass anyways. So the idea here is you gotta think in a reverse way. So you gotta think of it like, it has a boundary that it's never gonna exceed, and then since you have this boundary, you can just keep trying different values and then trying to reach the solution, but from like the end to the start, reverse order, sort of. A tip in Leetcode: always when you find that the solution is crazy and like illogical, such as, it's not illogical, but when you find like solutions are getting out of hand, like you gotta distribute cars over ranks, there has to be a simpler way. Like, you have to think reverse, or you have to find another way to attack the problem. So in this case, the minimum time taken to repair all cars, what's the worst case it could be? The worst case it could be, let's say if we had all these cars and we had only one mechanic, right? So it's gonna be r times n squared. So it's gonna be 10 squared times r, whatever the rank of him is. So the maximum of these ranks, the worst mechanic, the last mechanic, times all of the cars. That's the worst it could be, because there's no, how could it be worse if the worst mechanic takes all the cars? That's the worst scenario, right? So that's basically the minimum, the maximum minimum time taken. So that's the worst one. We don't want that. We want to minimize that number as much as possible. So we have the boundaries of the minimum time taken, which is from 1 to like that maximum, right? And then we're going to keep trying. We're going to do a binary search on that, and then we're going to keep trying. And every time we land on a time, we're just going to check, is this time feasible for all the mechanics to finish X cars, and then check if X is greater than or equal to this, essentially. So this is how you reverse the problem. So in our case, we have this isValid function. What does it do? Let's say we have a binary search. We're binary searching on that. I said max ranks cars times cars, which is n squared, right? We have an n, which is a minimum time candidate. We're going to check it in isValid. What we do is we keep counting the cars each mechanic can do in that time, basically. We loop over the ranks, right? And then we have this equation, right? So r times n squared equals the time, basically. We have the time and we have the r. We just need to get the n squared. So we divide them. So we divide the time over r, and then we do the square root to get the n, right? And that's what we did. We get the square root of it, and then we just have to floor it, because let's say a time of 14, right? A time of 14 in this case with rank 4 would yield me like 10.7, and then 10.7 that means it didn't do 11, it did 10, because it couldn't do 11 and 14, basically. So then you have to floor it, because then the best you could do is 10, right? So we floor them, and we keep counting the cars, right? And then if we find out that, okay, we can do more than 10 or 10, that's good. That means we can actually move our pointer backwards here and keep searching for a better solution, if there is. And eventually it might land on one that can do exactly 10, right? And then we just return R plus 1 in the end. And that's how it works, basically. This is how the idea of the trick is to know how to use binary search more in this solution, more than actually solving it. You gotta have a range. So you gotta have this. You gotta have, sorry, this array, and then this value, and then there has to be an upper bound to this. There has to be some upper bound to the actually the thing that they are asking from you. There has to be an upper bound, and then you work backwards. So yeah, this is in obviously n log n time, because we binary search, and for every binary search we actually loop over the array, calculate the car count. So that's been it, guys. Thank you, and see you in the next one.